We have started recently to analyze for emissions, mostly because as you start to take things from the lab scale to the field scale, of course, getting regulatory approval, emissions are a very important component of that. And also, some people have been asking the question, well, how do you know you're actually destroying the mass? What if you're actually emitting it and most of it's just being emitted and not actually being converted to carbon dioxide and water? And so we wanted to look at that, and so I only have some very preliminary results here, but basically what we have is we had to develop a new kind of experimental apparatus, because basically gas analysis from a combustion reaction is extremely difficult. You have a lot of gases being produced, a lot of steam being produced. It's hot, and capturing all of that and analyzing it carefully is very challenging. So we built a whole new apparatus just for doing that. We weigh the sample in time, so we know the actual mass loss as a function of time, and we look at the mass being accumulated in our chimney. And here is one example result, a preliminary result, being written up for a paper right now. So here is we're analyzing for total VOCs. This is for an oil sludge. We're quite interested, I'll show you for one of our projects in treating soil contaminated with hydrocarbon, basically crude oil sludge, very heavy crude oil. And what you see here is the range of compounds that are detected from a full suite of VOC analysis. So we're seeing here on the order of 15 compounds out of all 63 that we measured for. And you see some of the typical compounds that you're familiar with: benzene, toluene, the BTEX compounds, heptane, hexane, some unusual ones, for example, propene. And what you see is that we get a range of these compounds coming out, and this is total mass emitted over the length of an entire column experiment. And you see that we did it at 3 different airflow rates. So we're looking at it as a function of airflow rate. And as a function of airflow rate, we see very little sensitivity, but we do get a decrease in most of the compounds as you increase the airflow rate. So that's suggesting that as you increase the airflow rate to this oxygen-limited reaction, you're getting more complete combustion, which means more complete conversion of the hydrocarbons to CO2 and to energy and to water, and a little bit less emitted in terms of volatiles or partial combustion products. Okay. Now what we do is we add so for example, the blue bar graph here, the blue is one experiment. If we add up all those blue curves to get the total mass emitted as VOCs, and we take that as a fraction of the total mass we started with, in terms of carbon, we get the fraction of mass emitted as VOCs, and that's what we see here. And here's a range of uncertainty, given uncertainty of our experiments, and we see basically that on the order of 0.6% of the initial mass for all these 3 experiments, this is injected airflow rate versus percentage of emitted as VOCs. We see on the order of about 0.5% of the initial mass is being emitted. That means 99.5% of the mass is being consumed and destroyed in situ by the combustion process. So it's extremely efficient. So that's very encouraging. We may still need to do gas capture. We may not want to let any VOCs into the environment. We may not need to do VOC capture in the field, depending on what kind of environment and the regulation limits. But capturing and treating a very small amount of mass is very straightforward, off-the-shelf technology. And it's nice to know that most of it is being destroyed. Now here's a separate study where we were being asked to treat some soil. You see it's a very silty, clayey type soil that was contaminated with creosote. Now creosote has chlorine in it. It's a chlorinated compound. And when you have chlorinated compounds in heat, then you need to worry about the formation of dioxins and furans. And in fact, as you see here, there's about 30,000 milligrams per kilogram TPH in the soil, but there's already 5,000 nanograms per kilogram of dioxins in the original soil. So the question is, what's going to happen to those dioxins? And this was an industrial, a site owner wanted to know before they considered STAR for their site. So we did a very detailed study in the lab where we did a treatability study, and we also measured the gas phase. We did a very special test for dioxins and furans. And what we saw that in the soil afterwards, there was no TPH left. You can see what the soil looked like here. It kind of got treated in chunks because it's kind of clayey. It was all treated, and we ran it with a sort of chunky material at the end. And the soil went down to 13 nanograms per kilogram. So the question was, where did those dioxins go? And when we analyzed the vapor phase, we could see that there was virtually nothing in the vapor. We had this one, we had basically the same value as the blank. And so what that tells us is that the temperature was sufficient essentially to destroy the dioxins. So that was very encouraging as well. And it's not surprising because the temperatures reached here were on the order of 700 degrees Celsius, which is typically the type of temperatures that you would use to destroy dioxins in an incinerator anyway. So we basically have an in situ incinerator. So just to conclude from what we've done so far, you can get a range of VOCs emitted because you have a heating front advancing, and most fuels will have some volatile components, and some of those will be emitted, and those will depend on the type of contaminant that you have. However, the amount emitted from the studies we've done tends to be on the order of less than 1% of the total mass, and for the tests that we've done now, we haven't observed any dioxins being emitted from chlorinated materials. So that's it on the emissions experiments. Although I'll have more to say about emissions when I come to the in situ test. I'm just going to check to see if there's any questions at this point. So I have one question here. It says, how do you avoid losing control of the smoldering reaction? That's the first question. And the second question is, where does all the carbon dioxide go? So the first one is, how do you avoid losing control of the smoldering reaction? And I don't know if you were here when I was speaking earlier, that the reaction can never get out of control. Smoldering is an oxygen-limited reaction, and when you turn off the air that you're injecting, you're forcing air into the pore space. When you turn off the air, the reaction always shuts down, and we've proven this many, many times. So you're controlling the rate of reaction and the propagation of the reaction by the airflow rate that you're injecting, and once you turn off the air, or when the NAPL is completely gone, the reaction automatically shuts down and everything starts to cool. So that's the first question. Where does all the CO2 go? That's a good question. At the moment, the CO2 gets emitted. And obviously that's not ideal. We wouldn't like to, if I could choose otherwise, I wouldn't want to be emitting CO2. But that is a consequence of this technology, that you are converting essentially the carbon compounds into CO2, water vapor, primarily, and energy. And the CO2, unless you set up a CO2 capture system, which is not off the shelf, then the CO2 does get emitted. Now, I'll show you in in section number 7, I'll show you a sustainability analysis that looks at the CO2 emissions and how serious they might be. And hopefully it'll alleviate concerns that CO2 emissions are a real sustainability concern for STAR, because in fact, when you compare them to any other treatment technology, the CO2 actually turns out to be very, very low in comparison. And we'll talk about that in a moment. So thanks for that question. So we're going to go and talk about treatability studies briefly. Pretty much any kind of remediation technology generally has a treatability study. That means you take contaminated soil from a real field site, send it to the location to do the treatability study, and they can tell you whether your contaminant, your soil from your site, is suitable for this kind of technology. So, of course, we've developed that for STAR, and it's available for bioremediation and for ISCO and for everything else. And a lot of the research it's important because a lot of the research I've been showing up to now has been with artificially or synthetic contaminated soils. We buy coal tar, we buy crude oil, we buy diesel or whatever, and we mix it with soils ourselves, so we know the amount of contamination, we know the source, and then we treat them for research purposes. So this is important for me to show you what we've done with real soils, all the treatability studies, we give back results to the clients on the amount of airflow, the ignition characteristics, the fuel content, the moisture content, the byproducts in soil and in gas, and whether STAR is self-sustaining for your material or not. And so far, we've received 17 different batches of soil from around the world. Usually we get 1 or 2 buckets worth of soil that gets sent to our lab here at Western. And we basically do a standard column experiment on that soil. And these are just some of the results I can show you. Here's some coal tar soil from the United States. Here's some oil sludge, contaminated soil, also from another site, United States. We've had material come in from Europe, from Belgium. Here is another coal tar site. We've had things come from Australia, from United Kingdom, places in Canada, and pretty much the results are always the same. For all the soils we've received so far, we've had self-sustaining combustion, and we've had complete destruction of everything that's been in there. So, for example, here's a list of, I think, the 15 or so that I could fit onto the slide. And you can see that we've had a range of different contaminants. Sometimes we don't even know what they are. They're just a mix of various things. This came from an oil waste company. They go around and they just pick up oily waste and they incinerate it. Incineration is an extremely expensive process because you're always adding energy continuously. So they were interested in whether STAR would work for their material. We've got tars, creosote, coal tar. This is the one where we did the dioxin furan testing. And you can see we've had self-sustaining combustion in all of them. We've basically had a huge range of starting concentrations right up to this incredibly contaminated material from Australia. And you can see that basically nothing left in the end. So it's been a very, very successful way of demonstrating the viability of STAR for real sites. And I want to go into more detail about 2 of these in particular. This silty sand coal tar site in the U.S., it was this treatability study that really led to the success here, led the client, DuPont in this case, to invite us to do an in-situ pilot trial. So I'm going to talk about that pilot trial. And it was this success with a large oil company that was looking to clean up, it's got tank bottoms. Basically, they have, they store their crude oil in large cylindrical tanks, and every month or few months, those tanks need to be cleaned out. In the bottom of those tanks is a sludge that can't be transported to the refineries. It's basically a waste, and the key was to try for them to figure out what to do with this waste, and they wanted to know if STAR would work for their waste. So they want to treat that waste in an ex situ manner, so I'll be talking about the ex situ test associated with this petroleum hydrocarbon contaminated sludge. So just to briefly summarize the treatability studies, we see that STAR works on a wide variety of highly recalcitrant compounds, various different soil types from around the world, and these laboratory studies have been really useful to see that STAR really applies to a lot of these sites and for generating interest to take it to the next step of moving up to a pilot trial. Now, I know that normally when we're teaching in front of a class, we take a break, but if nobody minds, I'm going to continue on here because I know that you can pause and you can continue watching this later. So if you need a break, you feel free to take a break. But I'm just going to keep on going because, again, I have a lot of material and I want to make sure I get it in the right amount of time. So feel free to hit pause if you want to, but I'm just going to keep on going. So, in-situ pilot test. So this has been a really exciting part of the development of STAR. This is our first chance to try to actually ignite a self-sustaining smoldering reaction in the subsurface. This is a DuPont site. It was acquired by DuPont. I give them full credit. They aren't responsible for contaminating this site, but they acquired it when they took over a company. You can see this is in New Jersey, in a very highly industrialized part of New Jersey. This is, I'm sure all of this area is contaminated, so not just this one area here that we focused on. It's a 37-acre site, and it used to be a former chemical manufacturing facility. So there was all sorts of chemical manufacturing processes here, and coal tar was one of the byproducts. And what they did on this site, it was they dug, so the processes were going on. Right now you can see containers on here because it's a container storage site for shipping containers across the ocean. But under the ground here, or before there used to be a whole bunch of chemical manufacturing facilities here. And around the edge of the property, they dug lagoons, which means they took a backhoe and they dug basically pits around the edge of the site, and they used that to dump their waste. And so they had waste, a lot of coal tar waste, that they dumped into these lagoons around the edge of the property. And then what happened was they bulldozed the property, and they bulldozed all the buildings, the bricks, the cement, and they got a bunch of industrial fill, and they basically filled in the site and just covered it all up. And these were those magical type of lagoons that I'm sure you've heard about if you've been in the remediation industry or the contaminant industry for long. They're the type of lagoons that would never fill up. So they're kind of magic that way. They could just keep dumping material in them, and the level in the lagoon would never overflow. So it was very useful, but one had to wonder where that stuff was going. A large site investigation by the Geosentech team has estimated there's about 55,000 cubic yards available for treatment by STAR. That's how much that's the actual NAPL contaminated volume in the subsurface, if you can target it with an in-situ technology. But of course, the only site remedy available for this site is excavation and removal. And they've estimated that they'd have to dig up about 300,000 cubic yards to remediate the site completely and get it up to site standards where they could sell it for reuse and redevelopment. Now that 300,000 cubic yards of, you can imagine that's on the order of $50+ million. And so you can see there's a big incentive for companies to look for less costly and less hazardous alternatives, in situ alternatives. So the objective of the pilot testing was really to try STAR for the first time at a large scale, to develop a down well ignition and air delivery system, because we obviously, we're not going to do it the way we've been doing it in the lab. Also to, the water table is very shallow here. So we're now going to be doing STAR for the first time below the groundwater surface, and below the water table to see if STAR was viable. And we really wanted to quantify the mass destruction rate and the remediation efficiency. So this is what the site looks like. Here's the site map I showed you earlier, and here's the industrial fill, which is about 1 to 3 meters deep on the site. And beneath that is this peaty clay called the meadow mat. And it's a clay that's thin at one end of the site and much thicker across the rest of the site. And when we did some detailed site investigation, we found a window. And you can see the window here, and that's another word for a hole, in the meadow mat. And that wasn't discovered previously. And this is exactly where the lagoons are. There's about 1, 2, maybe about 6 lagoons around the edge of the property here. And there was concern then that the contamination in the fill layer, the lagoon, the coal tar, might have percolated down into this underlying sand unit. There's an aquifer down here, and underneath that aquifer is a silt and then a till. So that's the subsurface. And here's, we have a very good understanding of the distribution of coal tar using a technology called Targost. Targost is is a sort of a direct push fluorescence technique that's very good for detecting coal tar. And you get a distribution of coal tar. So here we can see this is the coal tar that's within the fill unit. And now we have seen that there's a lot of coal tar also at depth, significant depth, below the meadow mat, and in that underlying alluvium sand. So both of those are concerned. Both of those will need to be treated. So we did 2 different pilot tests, one shallow and one deep. So I'm going to show you the shallow one first. This is the way STAR would look for a shallow application. Well, actually, it looks pretty much the same for a deep application, to tell you the truth. It looks the same. Basically, what you do is there's a 2-inch diameter well that's put into the center of the coal tar zone near its lower extremity, because we want to clean it upwards and outwards. And we lower in our special star tool into that hole, and we have a screened interval across the contaminated lower end of that section. So here we're cleaning, for the shallow test, we're cleaning above the meadow mat. That's the clay here. And you can see it's about 3 meters depth down to the clay, and there's about 1.5 meters of very significant coal tar contamination. The water table is about 1 meter down. So we're operating here right below the water table, and we're igniting down here, and we expect the reaction to propagate upwards and outwards, because we're also going to inject air into through the same screened interval, and we're going to turn off the igniter. We have thermocouples located all over our site, and basically what we have is an air sparging system at this end, and a vapor capture and treatment system this end. So the air sparging system is off-the-shelf technology. The vapor capture and treatment system is also off-the-shelf technology. For example, for air sparging, you have to capture and treat the gases, right? So the only unique part is this, basically the new star ignition and air delivery tool that we've developed. So that's what you see. That's what star looks like in both configurations, and the only difference is the depth here. So this is what the shallow system looked like. In this case, we drove sheet piling into the right from the surface down into that meadow mat. And the reason we did that is because we're cleaning up a very small part of a much larger lagoon. And the key thing was for us to separate the part that we're treating from all the rest of the coal tar, because we wanted to be able to clean it up and show that we've cleaned it up. And if you don't put in sheet piling, then very likely, as soon as we stop treating it, fresh coal tar is going to flow back in from the outside, and we'll never know that we've cleaned it up. So that's why we put in the sheet pile. It was a 6 meters wide by 18 meters long, and we basically treated it with 2 injection wells, two ignition wells. The rest of all this is thermocouples. 3 meters depth. Now that was phase 1 and 2. We actually did two phases of testing in that cell. We did a single ignition at a single well, and then we ignited both of the wells to try and clean up the entire cell. Then we did the deeper unit. We did 7.5 meters below the water table. So we're looking at about 25 feet down for the Americans in the crowd. And in this time, we decided to try it with no sheet pile, because, of course, in a full-scale application, there's not going to be any sheet pile. And the only thing that you see here is this mat, which is our vapor collection system. There's pipes underneath the mat to collect the vapors, because for these initial trials, we wanted to capture, of course, all the gases, so we could measure CO and CO2, and also run all the vapors through activated carbon. So we knew exactly what we were getting, because these are basically large-scale in situ experiments. So this is what the pre-pilot characterization looked like at various places around the shallow fill unit. You can see pretty much everywhere we looked, we had nasty, mobile, highly saturated coal tar. It was pretty disgusting. This is what the site looked like. Here's the sheet piling driven into the clay layer. This is basically an off-the-shelf air sparging system. Here's your compressors, and it's delivering the air through this manifold. We actually have 9 injection wells here, but we actually only ever use 2 of them. And then we have a cap on top with pipes underneath that basically collect all the gases through here. Here we're measuring the integrated CO and CO2 and the VOCs of all of the collecting gases, so we know everything that's coming out. These are water knockout tanks. We were worried about having a lot of water vapor. We hardly even used them. It basically didn't have a lot of water vapor. And here is the activated carbon. So everything went through activated carbon. Oh, there's actually also a cooling tank, because you have to have cool gases go into activated carbon. You can't have hot gas. So it cooled the air, and then it went through activated carbon, and then it was released through a stack. And we had big monitoring truck here that was actively monitoring for absolutely everything, temperatures and gas concentrations. And this is the major result from the test. This is actually from phase 2 when we got the go-ahead. We had a very successful phase 1. This is phase 2, and what you see here is we had a preheating period here. Let me talk about this in a second. Blue is plotted on the right-hand axis here. This is days after ignition. So this is after we started blowing air and turned off the igniter. Okay? And this is the rate of mass destruction in kilograms per hour, computed using the CO and CO2 that was produced. We know the stoichiometric ratio between coal tar destroyed and the CO2 produced. And what we see here is that we get mass destruction rates that continued throughout the self-sustaining burning period of about 10 days on the order of which ranged between 25 and 45 kilograms being destroyed every hour. We had a very strong self-sustaining reaction inside the unit, the fill unit. And it was, I don't have the maps here, but it was basically propagating outwards through a highly permeable reaction zone. I mentioned about those bricks. Well, we found out when we excavated later that there was a very large brick layer that had been pushed into this lagoon, and we were smoldering right in the middle of that. And the reaction propagated through these bricks and smoldered out, and then it also propagated, so there's a brick zone, and then there was a sandy fill zone, and it propagated outwards from that as well. So we had a very good distribution of the reaction, propagating in multiple directions, and we had this very good variable destruction rate as various, as the front moved in different directions and traveled through these different zones. On the left is an integrated total mass destroyed over the length of the test. And what you see is we essentially, with some uncertainty on it, estimate that we destroyed on average about 4,500 kilograms of coal tar over about 11 days, which is actually, pretty fast for a remediation technology, particularly an in-situ remediation technology. Now the question was, what about the vapors? How much of that was emitted and how much it was actually destroyed? So we actually measured everything that was emitted. It's just like I showed you for the lab experiments, and we get almost the exact same ratio. 1 kilogram of total VOCs, you add up all the VOCs, emitted for every 160 kilograms coal tar that was destroyed in the subsurface. So again, it's on the order of 0.5% that's being emitted, even at this large scale. So that was very encouraging. And when we go back, and here's a top-down view of the cell, and we took cores, split-spoon cores, from various locations. You'll see here's a before and an after from one location over in one corner, and you can see basically afterwards we get very similar results to what we're getting in the lab. We're getting, basically a clean, totally clean sand. In fact, we were getting this goopy recovery before, and now we're starting to get, it's actually getting hard to recover because it's water-free, and it's also organic content-free, so it's just basically falling apart. It falls out of the split spoon. Here's another example from this end of the contaminated zone. You can see what the drill, this is we were installing our wells, the rotary drill looked like, and basically the hole fills right in with liquid coal tar. And afterwards, you can see here, we have very clean sand, and as I said, we're getting poor recovery because of this very friable, remediated sand. And this, you can see, is the interface with the PD clay. So we've driven down through this alluvial fill. Sorry, not alluvial. This is the human, I can't think of the right word, but human deposited fill. And here's the natural clay. And you can see the transition here. Our treatment zone was right at the interface here. We were treating upwards. So we're getting very good results. Here is a table of all of the compounds that were analyzed for in the before and after. This is now soil analysis. So the numbers here don't really matter. We have big numbers before. We have very small numbers afterwards. And and you can see that we're getting similar results to the lab. This is 118,000 milligrams per kilogram before, and on the average, we're getting about 258 milligrams per kilogram afterwards. And the New Jersey, this is the New Jersey site, the New Jersey department criteria is you have to get below 4,300 milligrams per kilogram in your treatment system. So, where STAR traverses the subsurface, it's very, very effective. So, to summarize the shallow test, 1.5 meters below the water table, on the order of 5,000 kilograms destroyed in about 12 days, 3 to 4 orders of magnitude reducing in concentration. We had about 30 feet propagation, that's about 18 meters from one end of the cell propagated right across to the other end of the cell. And it probably only stopped there because of the sheet piling walls. We had silt, sand, and bricks all in this cell. It was a mess. We had destruction rates on the order of 800 kilograms of coal tar per day, emanating outwards from a single ignition well. Oh, and I didn't show you the sustainability analysis. Where is that? I think I put the slides for the sustainability analysis at the end of the next set of slides. So it's coming up in a second, but you'll see that it's very favorable. Okay, I'll talk about the deep sand test now. In this case, we had no barrier to groundwater flow, no sheet piling, and we were doing it much deeper than we'd ever did it before. This is 7.5 meters below the water table. You can see what the pre-test cores looked like. It was a mess down there. And this is just to show you what thermocouple data looks like from the subsurface. Here's where we're doing the preheating. You can see when we turn on the air, we get this sharp spike in temperature, just like we expected. Now, we're not getting the same kind of peak temperatures. We're only getting up to 500 degrees. That might be a function of, I think I showed you before, when you have significant water content, it decreases your peak temperature, but doesn't mean that you can't do self-sustaining smoldering. So we're having lower peak temperatures here of only 500, but here we see a propagating front from one location to the next, and here we're getting the elevated CO2 concentrations emerging at the surface already. Remember, we're only doing gas sampling now at the surface, which is 8 meters or 9 meters higher than this location where we're measuring these temperatures. And here's a map now, excuse me. Here's a map of the propagation of peak temperatures looking down from the surface, irrespective of depth. We have thermocouples at various different depths, but what we're just doing is taking any depth and showing because we want to look at how the peak temperature propagates outwards from our ignition well. There's only a single ignition well, and it's located right here. So you see, it's not a homogeneous distribution of temperature, but it is fairly spherical, moving outwards from our test. These are the locations of the thermocouples, and this is now in feet. Sorry, but we plot this up for an American company, so everything's in feet. And you can see that at early time here, after 1 day, we have an ignition zone that's on the order of maybe 2 feet in radius. And now, if we go to day 6, we see a very, very uniform spherical combustion zone that's radiating up to about 12 feet from the ignition point. Now, if we look, here we're at sorry, that's day 6, and now at day 11, you can see, really remember 450 now. If 500 is our peak temperature, then 450 probably represents our very strong smoldering zone, and you can see that that zone is propagating, all the way out to the edges of our anticipated treatment zone. Here's what it looks in cross-section. Here on the right-hand side is the Targos profile. Now this, where you see spikes here, it means coal tar contamination. So we have peaks in coal tar contamination here, a very hot zone at this depth. Then there's this is a clean zone here, a clean horizon here, and then another sharp zone here. So we were targeting this lowest contaminated region. And so that's why we did our ignition right down here at the bottom. And in cross-section, what we see is that the combustion front propagated outwards and upwards right to the edge of this clean zone. And what we believe happened is that, in fact, there was not enough fuel in this clean zone, and the reaction propagated outwards and upwards and stopped. It self-terminated at this clean zone. So what it means is that to clean up this zone as well, we'd have to raise the tool up to here, make sure we have a screened interval at this location, and then start a second reaction here, and have it propagate upwards and outwards at this location. This is the Targos before, and then we did another Targos profile afterwards, and you can see virtually nothing in the treated horizon down here afterwards. So very, very successful test. And here's what the cores looked like. Here's a core from this zone here, and here's another core from this zone. So this is about 6 feet northwards of we're looking in plan view. This is 6 north of our ignition point. This is about 12 feet westwards of our ignition point. You can see very, very clean alluvial sand, which is very much like what we see in the treatability studies. And here's another one from very close into the combustion zone. Very, very clean treated soils. And in terms of soil concentration, we're getting about 18,500 milligrams per kilogram before and about 160 milligrams per kilogram afterwards. And so it's about a 99-ish% reduction in concentration. So very, very encouraging results. So what we've seen for our pilot scale test so far is for the deep one is that we've had stars successfully ignited at 7.5 meters below the water table. We see a 3 to 3.5 meter radius of influence. That's a mistake. I think that should be at 12 days, not at 6 days. And we see that given the soil type that we had there and given the air injection rate that we used. We saw about 0.5 meter per day propagation rate of the reaction front, and we had treatment of about 800 kilograms in total over about a 2 meter thickness of coal tar from that single well, and about a 3 order of magnitude concentration reduction. So very, very promising results that we can treat things both at shallow and at deep depth. Now, I just want to talk about the sustainability analysis. As part of proposing to roll out STAR for the entire site, DuPont, to their credit, is very concerned about how sustainable various treatment options are. And they have a policy to always choose something that's the most sustainable. So here's a independent sustainability analysis that was done. It's done using a sort of an industry standard program called SEMA Pro. And the way SEMA Pro works is that it evaluates different technologies for their sustainability, and it basically accounts for every single part, every aspect of the remediation technology. So it considers all the electricity used, it considers all the PVC, polypropylene, and water and steel that's been used, it considers all of the miles that will be driven by the trucks, it considers the source of the energy that's being used to drive the system, everything. And it converts everything into a number of different factors. I've only shown one of those factors here, and that's carbon footprint. And that's because a lot of people are concerned about the carbon, the CO2 that's being emitted from STAR, and that's a perfectly reasonable concern. What we're looking at here is the carbon footprint in equivalent, so everything's been turned into tons of equivalent carbon dioxide. So if you have some other processes, they're converted into CO2. And here we're comparing STAR. It should be LTTD, low temperature thermal desorption, which is one possible remedy, and excavation disposal, which is, for this site, really the only possibility. And what we see is that STAR compares on the order of 10 times less than these other technologies. And that's because, of course, excavation disposal involves a lot of material being brought up. So both of these involve excavation. Excavation is extremely energy intensive, somewhat hazardous. This one would be an on-site treatment. This would be an off-site treatment, so you'd have all the truck miles being driven to the landfill. But STAR, of course, has embedded in this all of the CO2, all of the coal tar. It's assuming that all of the coal tar is treated is converted to CO2. Now, the program also has the ability, because some of the input parameters are statistical. I mean, we don't know exactly the number, we have a range of numbers. So you can actually input a range of values for every input parameter, and it'll then run thousands of stochastic analyses to look at what the distribution, the probability distribution would be for that carbon footprint. Because we know it's not a single number, but it's a probability distribution. So what you see here is the probability distribution. There's a very, very high probability and a very narrow distribution that the carbon footprint for STAR will be well below 10,000 tons equivalent CO2. Whereas you can see that there's more uncertainty with the LTTD and the excavation because of various uncertainties in various parameters. But both of them are, up in the 40, 50, 60,000 tons equivalent. So this is, strong evidence that that even with the CO2 being emitted, still much less impact on global warming than these other technologies. And if you want to look at the breakdown of where the CO2 comes from, you can see here, for example, for STAR, we've got about half of the emissions coming from this directly from CO2 combustion of coal tar, and the other half from the electricity that's being used, but of course it's very little electricity because of the self-sustaining nature of the reaction, and some of the other materials that are used to install the equipment, to activate carbon that we have to purchase for treating the VOCs generated, things like that. In the low temperature thermal desorption, you've got the electricity used for the extraction and a lot of energy being used for continually vaporizing the contaminants that are being moved around inside the kiln, basically. And for excavation offsite treatment, we have all of that excavation energy that's being used. And then, this isn't disposal. This is offsite. This is taken to a soil treatment center, soil reclamation and treatment center. So, in situ STAR, we see it's very promising. That depth does not seem to be an issue. We have a new technology that we can now put 2-inch wells all across the site, and we can take our STAR tool and we can do an ignition in any one of those wells, and we can even do it at different depths. We're starting to define the rays of influence, at least for this site, is on the order of 3 to 3.5 meters per well. And so that tells us how many wells we actually need to install to treat the entire site. And of course, heterogeneity is going to be a factor. The alluvial sand, which is relatively homogeneous, had a very nicely defined treatment zone. Whereas in the fill unit, which is more heterogeneous, we had a more heterogeneous distribution of the air and therefore of the treatment zone. Ideally, coal tar has flowed into more permeable zones, similar to where the airflow can be delivered. You wouldn't expect a lot of coal tar inside the clay, for example, itself. So maybe these things can work together, but heterogeneity, like with any delivery technology, is going to be a factor.